Hi students, welcome to my YouTube channel. Today we are going to discuss the problems based on trusses. Okay, so here we have one problem, that is, consider the 4-bar truss shown in figures. That means here in this problem we have total 4 elements, that is 4 bar. Okay, so it is given that E, that is Young's modulus, 2 into 10 raised to 5 Newton per mm square, and area is 100 mm square. For all elements we have to find, determine the element stiffness matrix for each element. So in this problem, as we have 4 elements, so we have to calculate K1, K2, K3, K4. Then the second question, assemble the elemental stiffness matrix K for the entire truss. So here we have to calculate the global stiffness matrix, that is K is equal to K1 plus K2 plus K3 plus K4. Okay, then using the elimination approach, solve for the nodal displacement. As here we have total 4 elements, so we'll be having total 4 nodes. Okay, so each node will be having 2 displacements. Okay, so we have to calculate total q1, q2, q3, q4, q5, q6, q7 and q8. Then calculate the stresses in each element. So we have to calculate sigma 1, sigma 2, sigma 3, sigma 4. Okay, at the last calculate the reaction forces. So here we have to calculate R1, R2, R3, R4, R5, R6, R7 up to R8. So here we have the mechanism. Okay, so this is the figure in the question. So here this is the origin, that is node 1, and here it is fixed in x direction also, in y direction also it is fixed. Here that is node 2, here we have one force, that is 20,000 Newton, and here it is fixed in y direction, but in x direction we have roller support. Okay, so here again it is we have to find q5 and q6 here, that is unknown, and here we have one downward force, that is 25,000 Newton. Here it is fixed again in x direction and y direction, that is q7, q8. So at node 1 we have F1, F2, at node 2 we have F3, F4, node 3, F5, F6, and node 4, F7, F8. Okay, we'll start the problem. First we have to calculate nodal coordinate data. So for that we have to construct one table. Okay, that is nodal coordinate data. Okay, so here we have total 4 elements, and here we have to consider node 1, node 2, node 3 and node 4. Okay, so node number, then x direction, y direction. Okay, now I will write node number 1. You just check this node number 1, as it is origin, the x distance is also 0 and y distance is also 0. So I will write from x is 0, y is 0, as it is origin 0, 0. Now consider this node 2, this is the x distance, that is 40 mm, but y distance is 0 because this is in the same axis of the node 1. So for node number 2, the x is 40 and y is 0. Similarly for node 3, from this origin you can see this is the y distance and this is the x distance. X distance is 40 and y distance is 30 from the origin. So I will write here for node 3 40 and this is 30. Similarly for node 4, here node 4, this is the y distance and x distance is the same axis, it is in same axis, so x is 0. So I will write 0 and 30. So this completes the nodal coordinate data. For node 1, x is 0, y is 0. For node 2, x is 40, y is 0. Node 3, x is 40, y is 30. Node 4, x is 0, y is 30. Okay, next we have to calculate element connectivity data. Okay, element connectivity data. Again we have to construct one table, that is element, as we have total 4 elements, 1 2 3 and 4. Next, initial node and final node, then length of the element, then direction cosines, that is L and M. L, yeah, okay. Here we have to consider for every element initial node and final node. I will explain with the help of this figure. For this node 1, for element 1, this is the initial node, that is 1. 2 is the final node. If you consider element 2, 2 is the initial node, 3 is the final node. If you consider this 3, 3 is the initial node and 1 is the final node. If you consider this element 4, 3 is the initial node, 4 is the final node. That means starting point and end point. For this starting point, end point. For this starting point, end point. For this starting point, end point. So I will write the same thing in this table. For element number 1, initial node is 1, final node is 2. For second element, initial node is 3, final node is 4. For second element, sorry, initial is 2, final is 3. And then for third one, 3 and 1. 3, 1 and last 3, 4. Then we have to find the length. For element 1, 40 mm. For element 2, that is 30 mm. For element 3, here we have to apply Pythagoras, as it is right angle triangle. See here, if you want the length of element 3, that is square root of 30 square plus 40 square. Okay, 30 square is 900, 40 square is 1600. So you'll get 2500, that is after solving you'll get 50 mm. Okay, that is length of element 3. Similarly for fourth element, that is again 40 mm. Okay, so length is 40, 30, 50, 40. Next, here we have direction cosines L and M. Now how to calculate the direction cosines L and M? For that we have formula here. To calculate L, that is x of final node minus x of initial node divided by the length of the element. Similarly for M also, y of final node minus y of initial node divided by length. Okay, so for element 1, for element 1, L is equal to x2 minus x1 divided by length. Similarly, M is y2 minus y1 divided by length. Similarly for element 2, L is x3 minus x2 divided by length. M is y3 minus y2 divided by length. Similarly for element 3, L is x1 minus x3 divided by length. M is y1 minus y3 by length. For element 3, element 4, L is x4 minus x3 divided by length. M is y4 minus y3 divided by length. Now from this table we have to take x value as well as y value for each element 1, 2, 3, 4. Okay, now I will substitute the values. For L, x2 is 0, x1 is 40 and length is, sorry, here for x2 is 40, x1 is 0 and length is 40 for element 1. After solving, 40 minus 0 is 40, 40 by 40 is, we'll get 1. Similarly here, y2 is also 0, y1 is also 0, length is 40, 0 by anything is 0. For element 2, x3 is also 40, x2 is also 40 divided by 30. Okay, 40 minus 40 is 0, anything by 0 is 0. Similarly, y3 is 30, y2 is 0 divided by length is 30, 30 by 30 is 1. Similarly, for element 3, x1 is 0, x3 is 40 divided by length is 50. So 40 by 50 is minus 0.8. Similarly here, 0 minus 30 divided by 50, that is 30 by 50 is minus 0.6. Similarly for element, this one, element 4, 0 minus 40 by 30. Here this is also 40, 40 minus 40 is 0, 0 by anything 0. Here also 30 minus 30 by 0, 0 by anything is 0. Okay, now we have to write the elemental stiffness matrix, that is elemental stiffness matrix. So before going to write the elemental stiffness matrix, I will substitute these values in this table. For element 1, L is for element 1 L is 1 and M is 0 and this is 0 and this is 1, this is minus 0.8 is 1 and this is 0. Okay, so for this L, for that truss elements we have KE is equal to AE by LE, L square ML, ML, M square. Write the same thing here, L square ML, ML, M square. Now the same thing with negative sign, minus L square minus ML minus ML minus L square. The same thing here, this is M square minus L square minus ML minus ML minus M square. So this is the stiffness matrix for truss. Now we have to write the stiffness matrix for all 4 elements, K1, K2, K3, K4, that is for element 1, element 2, element 3, element 4. Okay, so for K1, element 1, for element 1, K1 is equal to, as area is 100 and Young's modulus is 2 into 10 raised to 5 divided by, that is length is 40, and here L square for element 1, L is 1, so 1 square is 1, then 0 into anything is 0. So minus L is minus 1, 0, 0, 0, 0, 0, minus 1, 0, 1, 0, 0, 0, 0, 0. Okay, after solving this, we will get 10 raised to 5. We'll get here 5, 0, minus 5, 0, 0, 0, 0, 0, minus 5, 0, 5, 0, 0, 0, 0, 0. As it is related to element 1, the first row indicates Q1, second is Q2, third is Q3, and fourth one is Q4. Similarly, first column Q1, Q2, Q3, Q4. Okay. Similarly, like that, we'll get K2 is 10 raised to 5. After substitution, we'll get 0, 0, 0, 0, 0, 0.66, 0, minus 6.66, 0, 0, 0, 0, 0, minus 6.66, 0, 6.66. Okay, as this is for element 2, so this is Q3, this is Q4, this is Q5, this is Q6. Similarly, Q3, Q4, Q5, Q6. Okay. Similarly, we have to write it for element 3 also. So K3, 10 raised to 5. After calculation, we'll get 2.56, 1.92, minus 2.56, minus 1.92, 1.92, 1.44, minus 1.92, minus 1.44, minus 2.56, minus 1.92, 2.56, 1.92, minus 1.92, minus 1.44, 1.92, 1.44. So this K3, element 3 is considered for node 1 and node 3. That's why it is 5, 6, that is node 3, and 1, 2, that is for node 1. Okay, similarly here 5, 6, 1, 2. Similarly, we have to write K4. After solving, we'll get 10 raised to 5, 5, 0, minus 5, 0, 0, 0, 0, 0, minus 5, 0, 5, 0, 0, 0, 0, 0. Okay, this is for element 4. So I will write for the in the point Q3 we have Q5 as well as Q6. At node 4 we have Q7, Q8. So similarly in column also Q5, Q6, Q7, Q8. So now I will write the global stiffness matrix. Okay, so for that global stiffness matrix, that is K is equal to K1, K2, K3, K4. This is very, very important. Okay, so here we have total 8 displacement values, Q1, Q2, Q3, Q4, Q5, Q6. So I will write K is equal to, as 10 raised to 5 is common, that is outside, Q1, Q2, Q3, Q4, Q5, Q6, Q7, Q8. Okay, so similarly here this position is for Q1, this is for Q2, Q3, Q4, Q5, Q6, Q7, Q8. see this is related to Q1, this row is related to Q2, this is Q3, this is Q4, this is Q5, this is Q6, this is Q7, this is Q8. Similarly, this column is for Q1, Q2, Q3, Q4, Q5, Q6, Q7, Q8. Just we have to identify Q1 column, Q1 row in these elements. Okay, here in this you can see here we have one Q1 row, Q1 column, this value. Similarly, we just verify Q1 values here. In second element we don't have any Q1 values. In third element we have this Q1 row and this Q1 column, that is 2.56. This is related to Q1. Okay, and in fourth element we don't have any Q1 values, so one element is 5 and another element is 2.56. so we have to add here, that is I will add 5 plus 2.56. Similarly, now we have to identify Q2 here, and here we are writing for Q1 only, so Q2 with Q1 we have to see. Here this Q2 with Q1, that is 0. Okay, then here Q2, that is second row, with Q1 is we have to write 1.92, not this 1.44. sorry, this is 1.92. okay, that is 1.92. next, this is Q1 row and Q3 column. Q1 row, Q3 column, here it is -5. okay, that is -5. and here Q1 row, but here we don't have any Q3. okay, now Q1 row, Q4 column, this is Q1 row, Q4 column, that is 0. and Q1, here we have Q1 but we don't have any Q4 column, so that is 0. Similarly, Q1 row, Q5, here we have Q1 row but we don't have any Q5 column, so if you see here, this is Q1 row but here we have Q5, that is -2.56. -2.56. Similarly for Q6, that is Q1 row, Q6 column, here we have Q1 row but we don't have any Q6 column, but here Q1 row, this is Q6 column, that is Q1 Q6, that is -1.92. -1.92. Similarly, Q1 row, Q7, here only in two places we have Q1. If you consider this Q1, we don't have any Q7. If you consider this Q1, again we don't have any Q7, so that is 0. okay, so this is also 0 because we don't have any Q8 values. So based on that, we have to write the remaining values. okay, so I will write 1.92, 1.44, 0, 0, minus 1.92, minus 1.44, 0, 0, minus 5, 0, 5, 0, 0, 0, 0, 0, 0, 0, 0, 6.66, 0, minus 6.66, 0, 0, then minus 2.56, minus 1.92, 0, 0, 7.56, 1.92, minus 5, 0, 1.92, minus 1.44, 0, minus 6.66, 1.92, 8.1, 0, 0, 0, 0, 0, 0, minus 5, 0, 5, 0, 0, 0, 0, 0, 0, 0, 0, 0. This completes the global stiffness matrix. Now we have to write the global displacement vector, that is Q. This is global displacement vector, that is equal to q1, q2, q3, q4, q5, q6, q7, q8, that is transpose. Okay, similarly global load vector, that is also transpose f, f1, f2, f3, f4, f5, f6, f7, f8, that is transpose. Here if you see this diagram, here f1, f2 is 0, here f3 is, this is 20,000 and f4 is 0, here f5 is 0 and f6 is, that is down, it is acting downward direction, so minus 25,000, and again here it is 0 and 0. If you consider the displacement, here it is fixed, and in x direction also, y direction also, q1, q2, 0, 0. Here we have roller support. In x direction we need to calculate the displacement, we have to calculate q3, so here only q4 is 0. Here we have to calculate both q5, q6, and here it is fixed, so q7, q8 remains 0. Okay, so first we have to write the equilibrium condition. Equilibrium condition, that is k q is equal to f. Okay, k means this entire matrix. Okay, the same thing we have to write whatever we have here. Okay, now here we have to write q1, q2, q3, q4, q5, q6, q7, q8, q9, that is equal to force, as f1 is 0, f2 is 0, f3 is 20,000 and f4 is 0, f5 is also 0, f6 is minus 25,000, it is acting downwards, and 0, 0. Okay, here as we discussed, we are doing with elimination method. Here q1, q2, 0, so I will eliminate these first two rows, first two columns. Okay, I will write here in short q1, q2, q3, q4, q5, q6, q7, q8. Okay, so I will eliminate first two rows and first two columns. So we need to calculate q3, so I want this q3. Here q4 is again, that is fixed, so I will eliminate this q4, this q4. Okay, so I want q5, q6 and q7, q8, both these are fixed, so I will eliminate q7, q8. So only remaining is q3, q5, q6. Here you just check it, we have to calculate this q3. I want this one, I want this one, and I want this one. Similarly here I want q3, q5, q6. So only we have to write this 5, 0, 0, 0, 7.56, 1.92, 0, 1.92, 8.1. Okay, after elimination only we are getting these 9 elements with q3, q5, q6. Okay, so after elimination 10 raised to 5, 5, 0, 0, 0, 7.56, 1.92, 0, 1.92, 8.1. Here q3, q5, q6, and load 20,000, 0 minus 25,000. Okay, first row into first column, second row into first column, third row into third column. After solving we'll get q3 is 0.04 mm, q5 is 0.00834 mm, and q6 minus 0.03284 mm. Okay, so we have to write these all displacement elements in single matrix, that is vector. Q is first is 0, second is 0, third one is 0.04, then fourth one is 0, then 0.00834, then minus 0.03284, then 0, 0. This is transpose. Okay, this is Q1, Q2, Q3, right? Q1, Q2, Q3, Q4, Q5, Q6, Q7, Q8. This is the nodal displacement vector for the entire structure. Okay, this is the nodal displacement vector for the entire structure. So similarly, we have to calculate stresses in each element. For that, we have formula sigma is equal to E by L minus L minus M L M. Here we have to write Q1, Q2, Q3, Q4. To that respective element, we have to write those displacement values. Already you know L, M, L, M for that particular element according to the table. So in this table, we have already calculated L, M values, that is direction cosines for all 4 elements. Okay, just we have to substitute all the values. So after calculation, we'll get, I will show you how to calculate for sigma 1. Sigma 1 is equal to, so E is 2 into 10 raised to 5 and length is 40. So this is minus 1, 0, 1, 0. That Q1 is 0, Q2 is 0, Q3 is 0.04 and Q5 is 0. So after solving, we'll get sigma 1 is equal to 200 Newton per mm square. So similarly, we'll get sigma 2 as minus 218.93 Newton per mm square. Sigma 3 will get minus 52.112 Newton per mm square. Sigma 4 will get 41.7 Newton per mm square. You just solve it and try to get these answer. And at last, we have to calculate reaction forces. You know already the formula for calculate the reaction forces at the support. So I will use this horizontal page. Support reaction. So that is R is equal to K Q minus F. Okay, so I will write the entire matrix here. R1, R2, R3, R4, R5, R6, R7, R8. So here 10 raised to 5. Here you will be having the total like Q1, I mean the first row, second row, third row, fourth, fifth, sixth, seventh, eighth. First column, second column, third column, fourth column, fifth column, sixth column, seventh column. Because already we have calculated the matrix here, the same matrix we have to write one more time. Okay, then here we have to write the displacement. Q1 is 0, Q2 is 0, Q3 is 0.04 and Q5 is 0 and Q6 is 0.00834 and 0.03284 0 minus force 0 0 20,000 0 0 minus 25,000 0 0. Here now how to calculate R1, R2, R3, R4, R5, R6, R7, R8. See, I will show you. If it is first row in this matrix, this is first row and we have to multiply with first column. For example, here we have the first element, this into this 0. Okay, then plus this second element into this second element in this column, third element in this row, third element in this column, fourth element in this row, fourth element in this column. Similarly, fifth and fifth, sixth, seventh, 8. Then whatever you will get the answer after solving this first row into first column, then minus this 0, you will get R1. Similarly with second row with this column, you will get R2. Similarly R3, R4, R5, R6, R7, R8 into this column, you will get the R1, R2, R3, R4. So here I'll give the answer, just verify it. R1 is equal to minus 15829.76 Newton, and R2 is equal to 3127.68 Newton, R3 0, R4 21871.44 Newton, and similarly R5 0, R6 0, R7 minus 4170, R6 sorry R8 0. This is Newton. Hence this completed the problem. Thank you.